Hello, welcome to a new episode. Today's topic is Principal Component Analysis Part 1, Principal Components. Today we'll talk about the principal components, also known as principal axis. We'll discuss about the representation of the data coordinates in the principal component basis. The principal component analysis is a procedure that transforms a set of observations of correlated variables into a set of values of linearly uncorrelated variables. The principal components are ordered from the largest variance to the smallest variance. The principal components are orthogonal to each other. They form a new coordinate basis. The principal component analysis can be applied for the exploratory data analysis and for making the predictive models. As a result of the principal component analysis, we get the loadings, which are the normalized principal components. Also, we have the variance along each one of the principal components. The transformed scores refer to the projection of the data coordinates onto the basis of the principal components. This projection is done by taking the inner product of the vectors. For example, let's imagine a two-dimensional data set which is easy to visualize. There can be as many principal components as the number of dimensions. So, in this case, there could be two principal components. The first principal component is along the direction of the largest variance. The second principal component is orthogonal to the first one. It is along the direction of the remaining variance. The transformation to the basis of the principal components is like rotating the figure. The axes of the figure are now the principal components. Now, let us briefly review how the principal components are calculated. One way is to apply the singular value decomposition to the data matrix. Another way is to apply the eigenvalue decomposition to the covariance matrix or the correlation matrix. In such a case, the eigenvalues are the variances and the eigenvectors are the principal components. Often the features are normalized to match the scales. In such a case, the principal component analysis becomes equivalent to the eigenvalue decomposition of the correlation matrix. In our example, we'll assume the normalization of the features. Examples. For this example, we have a dataset of the physical measurements of 252 males. We have 8 variables. We can apply the principal component analysis to any number of variables equal or larger than 2. We go to the PrimaXL tab, select PCA, and then Principal Component Analysis. We select the cell range of the dataset. We check on this box to output the result to a new sheet. Here, we leave all these boxes as checked because we want to have the output of the variance, loadings, centers, and the transformed scores. Finally, we press the Run button to execute. Great! At the top of the result sheet, we have the principal component variance. For example, the first principal component accounts for 68% of the total variance. The second principal component accounts for 19% of the total variance, and so on. Next, we have the coordinates for the principal components shown as column vectors. These are the loadings. Here we have the centers for the features. And finally, we have the transformed scores. Summary. Today we discussed about the principal components which can form an orthogonal basis. We could see that the principal components are ordered from the largest variance to the smallest variance. We could get the transformed scores by the projection of the data coordinates onto the principal axis basis. This was in fact similar to a rotation. Please visit our Facebook page for more information and videos. Also, make sure to subscribe to our YouTube channel. You can find the PrimaXL installer at our GitHub repository. Thank you so much. Until next time, bye.